All right, hey, I got a good one here on kind of one of my favorite ones is when something expands and you can get more volume in it, but it's got a little added twist. I don't know if you caught this. Let me read the question. It says most automobiles have a coolant reservoir to catch radiator fluid that may overflow when the engine is hot. If a radiator is made out of copper and it is filled with 16-liter capacity when it's at 10 degrees Celsius, what volume of radiator fluid would overflow when the radiator and the fluid reach its temperature of 95 degrees Celsius? 95 degrees Celsius operating temperature. Given that the fluid's volume, the coefficient of expansion beta is 400 times 10 to the minus 6, question mark. Note that this coefficient is an approximation because most car radiators have an operating temperature that is greater than 95 degrees Celsius. That's true. They're usually above boiling, I should say boiling regular water boiling, which is 100 degrees Celsius. And of course, you get away with that because you put it under pressure. And so the boiling point goes up. Oh, and you put in a coolant, which raises the boiling point. So it's kind of common to be operating, well, it's about 260 on the Fahrenheit scale. So that's about 50 above boiling water with a 2-to-1 ratio. So that's probably about 125, 130 degrees Celsius. So it is quite a bit more than what you would think just because of the boiling water. But again, the coolant and the high pressure can keep it a liquid at higher temperatures, and that way you can still cool your engine. Anyways, let me stay focused back on this one because I did want you to see, if you did quite catch this, I'll kind of make a container, and I'll just make it kind of a beaker-looking container instead of maybe a radiator. But the point is, if you fill it all the way to the very top, two things are going to happen, and I am hoping you see both of them. When you warm it up, of course, the liquid gets warm and expands, and that's going to be running out. So you might say, well, what runs out is the increase in volume of the liquid. However, remember that the container expands also. And I think that's why I'm getting some questions on this. This is easy to overlook. Plus, it might be kind of hard to calculate it. This is why I spent quite a bit of time on the video lecture about that ring with the sphere that you can put through, and was pointing out that the ring actually got bigger. A hole gets bigger when you warm it up. So a container actually can contain more when you warm it up. So I'm going to draw the beaker in green and then say there is a delta V. Now, maybe I shouldn't call it a beaker because this is the radiator. So maybe I should put underneath it that the radiator is going to increase its volume, and so is the fluid. So the net effect, the volume that actually, I guess, flows over the top would be how much more the fluid expanded compared to how much the radiator. And so actually, if the radiator expands more than the fluid, you wouldn't have anything flowing out. However, as we will soon see, most liquids expand more than solids. And so there's a really good chance this number, the expansion of the fluid, is going to be greater than the expansion of the radiator, which is made out of copper. So if we look at our thermal expansion, we said this coefficient is called beta. And if you take beta times the original volume and delta T, that, if we apply it to the fluid, is how much the fluid expands. But if we do the same thing here, beta, original volume, and delta T, and we apply it to, and I'll call it radiator, but I'm just going to put copper now down here because they make it very clear somewhere in here. Let me come back here. Radiator is made out of copper. Okay. So looking at these, you can see that the original volume, the open space, is going to be the same for the fluid as the open space in the copper. And they're both going to warm up the same amount. So I'm going to factor out the original volume and the delta T, and then put a beta of the fluid minus the beta of the copper. So the fluid, as they say in the problem, is 400 times 10 to the minus 6 for each degree Celsius. Now, they don't give me copper in this problem, so I think I need to go grab the textbook. Here's chapter 13. And somewhere in here was this table. I guess it was table 2. And they say here is the coefficient of linear expansion, and here is 3 times that for the volume expansion. And it looks like copper is down here, number 3. It'd be 51 times 10 to the minus 6. So 51 times 10 to the minus 6, also same units. And so it does match what I was saying, that the liquid is going to expand. See, 400 is about 8 times bigger than this 51. So there's going to be this overflow, but not as much as you would have thought had you not given room for the copper to expand. And that's, like I said, probably why people are giving me some questions like, well, what's this one for? And that's the extra space for the copper. Now, the original volume is the 16 liters, and it looks like we're warming it up. Oh, what did the problem say? We're starting at 10 degrees Celsius when we pour it in, kind of cold. But then we're going to warm it up to 95. So there's a change of 85. Okay, and I should put 85 degrees C so that the degrees C will cancel off and we'll be left with liters. How many liters here will be the volume? So taking the 400 and subtracting the 51, not forgetting that is times 10 to the negative 6. So that's the difference there. Then times the volume of 16 and times a temperature increase of 85. We're looking at just shy two, maybe 2 significant figures. So just shy of a half a liter. Okay. Hope that one helped.